the National Science Foundation has been funding dark matter searches for kind of a long time, and I wanted to see, well, where were the glimmers of light, and just learn more about how the field was progressing, what was happening, and what new imagination was coming in, and where were the difficult things to do, and what new levels were they achieving. And so I have been very excited all day. All the talks are very different. They offer very special perspectives on the dark matter search. And my hope, and it's actually my closing line of my remarks here, is that that you guys find it before I leave the planet. That's my request, because it is one of obviously one of the major questions of our time. And Elena, don't give up. We funded the LIGO experiment for 40 years, and they kept working the threshold lower and lower and lower the background, and voila, there you go. Lots and lots of merging black holes and neutron stars and all. So as a young astrophysicist, I was really inspired by Vera and her investigation of the universe. And I was really pleased that our paths started overlapping and we got to know each other. For her seminal contributions to astrophysics, the president awarded her the National Medal of Science in 1993. And I was really pleased to be a member of that committee on the National Medal of Science that proposed her, that nominated her to the White House. So that was my sort of first lesson learned as a new Penn State faculty member and head of the department, that you don't get prizes unless you're nominated. And then it helps to have a committee that knows about your remarkable achievements and puts you forward for these prizes, something that has really helped me in my future jobs propose other people who are distinguished and deserving. In the time since Dr. Rubin provided further evidence of the existence of dark matter, she has inspired a lot of our understanding of galaxy dynamics. And this continues to be an area of fundamental support by the National Science Foundation. So notable among the projects that we are supporting, let me see if I can get this in the right direction. I'll try, yes, there we go. Is the recently completed dark energy survey, which yielded the most accurate map of dark matter in the universe to date. Do we have, I missed a little bit of the middle of today. Do we have any people on DES? Great. Well, I'd love to talk with you at the break or dinner today. DES used the NSF-supported 4-meter Blanco telescope of the Cerro Tololo Inter-American Observatory in Chile, and I was really pleased the last time I was in Chile to see that this telescope that I used as a graduate student was now being used in a completely different way for something so important. In early measurements of the amount and distribution of dark matter in the present-day cosmos of DES are fairly consistent, as I understand it, with the results of the European Space Agency's Planck Observatory, but those of you working on it can tell me more. I understand that there's much more data to be analyzed, so that's just early results. It wasn't enough for Vera to relish in making her own distinguished mark on our field. She was determined to ensure that every woman who shared her aspirations and talent could have the same opportunities as well. So that leads me to this picture of the Georgetown Astronomy Department. Was anybody here at that time? From the looks of this photograph of the astronomy department, it's quite possible that Vera was often the only woman in the room, and I think some of us have been there. And we can say that is a distinction that one looks forward to outgrowing. question often for us is how to ensure more women have a seat at the table. And I think there's a lot of news in the press. Even today, somebody just sent me a few moments ago an article in Time magazine about this. So, once when Vera was asked why she was able to become a successful woman astronomer while so many other women ended up dropping out, she said that that's a question we only ask someone who has been successful. There may be hundreds and even thousands of women who would have made great astronomers and never really had the opportunity. They're the ones that ought to be asked what would have been necessary to make it possible for them to become successful astronomers. During Dr. Rubin's time here at Georgetown, as many of you know, she raised 4 children. I still remember the big long kitchen table. They worked on one end, ate dinner on the other end, each of whom went on to become a PhD scientist, mathematician. For a long time, the professional development track for researchers effectively penalized women who wanted to have families, and those problems persist today. Like Vera, it would have been impossible for me to walk my path if I had not been able to find a balance between my career and personal life. Many women in science aren't so fortunate. So NSF has adopted its programs to try to address these issues. Take our career awards, for example, which I'm proud to say were the first NSF awards received by many prominent scientists. Anybody here had in the past or presently a career award? Well, you know how important they are, and when I go visit universities, I always talk with the career scientists. I want to see not only what they're doing in research, but also in education. For a long time, early career translated into an age cap. That limited opportunities for women who took off time for maternity or family leave. So NSF streamlined and simplified the eligibility criteria, recognizing that early career faculty members have to develop their careers at whatever rate is appropriate to them, given their personal and professional choices. So therefore, we removed the qualifying dates for receipt of degree and first appointment. And then we had the Waterman Award, where we just made changes a couple of years ago, actually from just a very simple email request to me from somebody on the outside who said, having a cap has meant that out of 40 winners to date, you have vanishingly few women who have won that award. So we took a similar step. The very next year, after we revised the eligibility criteria, our winner was Dr. Christina Olson, shown in the middle here between Maria Zuber and myself. Maria was chairing the National Science Board at the time. She would not have been eligible had we not changed the requirements to give all people more time since earning their degree to make early career accomplishments. When it comes to the balance of work and family, sometimes science itself can help us level the playing field. Such is the case with the advent of telepresence technology, which is now enabling research vessels, for example, to communicate with scientists on shore in real time through streaming video and audio. Thanks to this new technology, Dr. Melissa Omand, an expectant mother and oceanographer at the University of Rhode Island, did not have to pass up on a career-changing opportunity to lead her first research expedition. She just did it remotely. And then there are research environments where no technology and only a firm policy position could be a remedy, which brings us to one of the most significant developments out of NSF over the past year, a term and condition added to all our new awards aimed at stamping out harassment, including sexual harassment. As both an astronomer and advocate for women in science, Dr. Rubin was a powerful example, reminding us to ask the right questions and to adopt or revise policies that are within our purview. Each of us has a responsibility for change and a unique frame of reference to affect it. And that's the biggest thing that I learned from that exercise, is that you can want to change the whole world, but based on wherever you are at the time, you have a very special role to play in affecting change, and you have to do what is within your swim lane. And within our swim lane was changing terms and conditions. So I hope it's making a big difference. There was just a bill passed out of the House this week, our Congressional House of Representatives, to have all the agencies adopt something similar to what NSF has done. As it is our common love of the cosmos that's brought us together, I'd like to discuss how NSF is helping to address some of our unanswered questions about the universe. For decades, our agency has invested in theoretical research into the workings of the cosmos, and we've built the observational infrastructure needed to test those theories. The universe echoes with messengers carrying information over billions of light years. As we're all aware, photons are messengers, as are cosmic rays and neutrinos. 4 years ago, NSF's LIGO allowed us for the first time to detect another messenger, gravitational waves. And we've heard a lot about gravitational waves here today, some very exciting results and theories, ideas were conveyed. So we, as some of you know, we launched something called our 10 Big Ideas, which was a strategic framework for the future that hadn't been done before at the National Science Foundation. We actually launched it 3 years ago, but we just started funding it with new monies last year. And one of them was the windows on the universe. It's the era of multi-messenger astrophysics. When we announced it, 3 years ago, even we could not have anticipated how soon we'd see new groundbreaking discoveries in the years that followed. So soon after that, the detection of the 2 neutron stars that we heard about today colliding in 2017, which involved photons and, thanks to NSF's LIGO, gravitational waves. And that marked the first observation of cosmic phenomenon through those 2 messengers. Now, some will argue that the sun has been communicating multi-messengers for a long time, and that's great, but not those 2. NSF's IceCube Neutrino Observatory in Antarctica played a pivotal role in the second discovery, helping to reveal, in collaboration with ground and space-based gamma ray observatories, a flaring blazar as a source of high-energy cosmic rays. And we continue to see new breakthroughs from the researchers and instruments that we support. The Event Horizon Telescope, this is the result. I think you saw it. It was on the front pages of newspapers all over the world, giving us our first ever image of the black hole. And the Chief Information Officer for the United States told me a week ago that was the most downloaded image in history. So she said, it's sort of quizzically, even more than the Mueller report. So. NSF supported the Event Horizon Telescope effort for almost 2 decades, and we were thrilled to share the stage with its collaborators when they came together to deliver this image to the world. As you know, we funded the LIGO experiment for 4 decades, so part of the answer to success is just to keep at it and trust in your investigators. And I have to give a huge credit to program officers at the National Science Foundation, because as you know, lots of people circulate in and out at administrative levels, in Congress, at our nation's great universities. And it's a few diehards that have been program officers for a long time that just kept really persisting through ups and downs and getting these things done. Behind the breakthrough of the Event Horizon Telescope was an enormous engineering challenge. There were a lot of technical challenges involved in linking a heterogeneous group of telescopes spread all over the world into one enormous virtual dish. For over a decade, astronomers and engineers and computer scientists traveled telescope by telescope, installing the atomic clocks, data recorders, and other hardware necessary for the task. And I can recommend a recent book by Seth Fletcher, who was, he's a Scientific American writer who embedded himself for 6 years with this project and just wrote a wonderful book. And I promise you, no matter what you do, whether you've been involved with this experiment or not, you will recognize those nights at the observatory and things falling apart and trying to patch them up and put them together. This experiment was actually very cheap by NSF standards. We only spent, well, something less than $30 million over all that time on it, but it leveraged telescopes that cost a whole lot more money all over the United States, like the ALMA telescope, right? That cost something on the order of $500 million and was a contribution of not only the US, but a number of other countries. And so, but they cleverly leveraged other assets in order to put this together. So they had to develop for each of the telescopes that were involved in this project special equipment. For example, at the South Pole, they had to build a new receiver to detect the radiation that they needed, and extra precautions to ensure that the equipment would work in the cold and harsh environment of the Antarctic. And then they carried that on, as you can see in reading this book about the black hole discovery, ensuring that eventually telescopes all over the world had great weather and could at exactly the same time be observing the same thing. So there were a lot of bridges of international cooperation that were built during this, which is another lesson you really learn in our business, which is the importance of international collaboration. Ultimately, a team of 60 institutes working in more than 20 nations contributed to the breakthrough. This map of NSF facilities illuminates the truly global nature of our work. To realize the full potential of multi-messenger astrophysics, collaboration with our interagency and international partners is vital. This was just as true of LIGO and the ice cube discoveries as it was to image a black hole. And thanks to NSF's sustained investments in multi-messenger astrophysics, we're poised to lead this burgeoning field for the foreseeable future. And I really like the part where the computer scientists have just contributed so much to our understanding of the phenomenon that we observed. I mean, imagine what the LIGO detections, even getting such an incredible facilities down to the level of threshold to detect something, if we didn't have the numerical relativists that really gave us the answer of what we were detecting. So we live at a very special time when we have the instruments and we have the computing horsepower. Now, the Large Synoptic Survey Telescope, which, as you heard, may go by some other name, which would actually please me because I find it a mouthful to say the Large Synoptic Survey Telescope. So the dark matter studies that were advanced by Vera have played a central role in the development of this facility, which is currently under construction on Cerro Pachón in Chile, and that construction is going very well indeed. And LSST promises to deliver a wider and deeper field of the universe, advancing observations from static images to a 10-year movie of the sky. The facility is an 8.4 meter class telescope with wide field optics designed to carry out surveys of nearly half the sky. And again, there's just going to be a tremendous amount of data that's going to generate. When completed, it'll produce a comprehensive data set enabling hundreds of fundamental studies in astrophysics. It has the potential to advance every field of astronomical study from the inner solar system to the large-scale structure of the universe. And of course, it has the potential to provide much-needed new information about dark matter through gravitational lensing and other means that we heard about earlier today. Private partners were integral in the early stages of the LSST and helped us get it going because they invested in the design and development prior to NSF's construction award, so that was essential. Today, the facility is a collaboration between the National Science Foundation and the Department of Energy. We're building the telescope, DOE is building the big instrument. So it's another of the many innovative partnerships NSF is taking across sectors. These are efforts that are at the core of our continuing growth into a more agile and responsive agency. We're hoping that the impact to the LSST will be just as far-reaching, and that's why we're working to ensure that the data will be made accessible to the community at large, from professional astronomers and citizen scientists to students and educators alike. want to share with you that I was recently at Princeton giving something called the last lecture, obviously not the last lecture for me because I'm standing here, but for the students. And I got a tour from Robert Digraph of the Institute for Advanced Studies and met two young astronomers from other countries there. And they told me that they had reanalyzed all the LIGO 1 and 2, the first 2 runs from LIGO. And so I looked at them like, oh, please don't tell me that you don't find anything there, and so on. And so I asked them, I said, well, did you find the sources that the LIGO team discovered? And they said, oh yes, and we found 6 more. And so they had, with their own techniques and using the supercomputer there at Princeton, they had their own algorithms for suppressing noise, and they had found 6 more identifications. So we just realized it's really important. Even the teams that work for years and years on these kinds of observations just can't discover everything. There's new imaginative tools that keep coming up. So the speed and depth with which LSST intends to map the southern sky will produce an enormous volume of data. We estimate about 20 terabytes or 20 trillion bytes of raw data per night. The facility is expected to catalog 18 billion objects in its first year alone. So it's no wonder that nearly half its cost during operations is dedicated to data management. We know that data mining or the exploration of large data sets can lead to these very big discoveries. So hence, that's why another of our big ideas is called harnessing the data revolution, because we just know there are so many issues like interoperable data sets that was talked about first thing this morning, to semantically interrogating data, to just putting together these vast amounts of data from all different sources. So we anticipate an era of very exciting discoveries from this instrument. Our agency-wide investments in harnessing the data revolution are aimed at developing an advanced data cyber infrastructure for researchers as well as a data-capable workforce. And that's something that our computer and information scientists talk to me about all the time, that they have an advisory group of illustrious scientists from all over the country that are describing the situation at our nation's universities, where we have a huge amount of students that want to, in all fields, not just in computer science, that really want to learn data skills, data analytics, and we don't have enough faculty to teach them, and the curriculum is in want of changes and so forth. So this is one of the really good issues of our times, that we have a burgeoning workforce. And NSF has always been, and I think other agencies really regard it as the science workforce agency, because as you know, we care about training of the next generation. So we've been trying to identify critical gaps in funding that next generation of scientists and engineers, and also all kinds of critical gaps. Hence, some of our other big ideas are identifying what's missing in our portfolio. So one persistent gap that we're working to address, and some of you may have applied for the opportunity, is the development and acquisition of mid-scale infrastructure for our research communities. The need for well-defined mid-scale funding program at NSF has been recognized by a number of boards and committees, including a decade ago, the 2010 Astronomy and Astrophysics Decadal Survey called New Worlds, New Horizons. The report had about almost 30 white papers describing projects that could be classified as mid-scale instruments and facilities, and recommended the establishment of a mid-scale innovation programs. But we just didn't have the wherewithal, the financial wherewithal to do that until recently. Some of you who follow budgets, hopefully none of you do. It's hard for me to imagine when I came into this job that the reason why NSF directors always talk about budgets and not science is because that's what matters there, is increasing the budget. But for the last the last couple of years, we have gotten increases in the budget, and so we were able to fund now to close the gap between really expensive stuff and really inexpensive things like spectroscopes that are in your laboratory, and to fund projects in the mid-scale regime. So this is the regime between $4 million and $30 million. So proposals, so we have had a very light, I'd call it a mid-scale light program in astronomy that we've been funding some things like looking at the cosmic microwave background, to enigmatic fast radio bursts, and the Event Horizon Telescope project would qualify as one of those projects. But and they produced really great results. But having the finally the funding to close the gap is really making a difference. So when the first thing we did was lower the threshold of our big projects to $70 million, and that was an important first step in shrinking the infrastructure gap, but it still left this need between a few million and $70 million. So what we wanted to do is seen in this, maybe, I don't have that picture, sorry. There's what we decided in the end to do was to separate that gap into two pieces, the cheaper pieces and the much more expensive pieces. And we published two mid-scale big idea solicitations last fall, and they resulted in more than 300 preliminary proposals, totaling a request for over $4.5 billion. So that shows how much demand there is to fill this gap. And since I kind of grew up doing instruments and thought that was an essential part of my graduate student career, and a number of other scientists have done the same, we just thought this is something we really have to do. So we have a house mark that's around $8.6 billion. We don't know if that will be our final budget for 2020, but we hope so, and we would put more money into the mid-scale. But right now, those proposals are being evaluated, these 300 preliminary proposals, and we anticipate making the first mid-scale awards this year. So I recently, that was just last week, had the opportunity to address the graduating class at Caltech. It was a great honor to be able to go back home for me to speak to the next generations at their commencement about the lessons I had learned. And one of those lessons was the importance of working on grand challenges from the outset in teams with interdisciplinary skills. And I was just very pleased. I gave some examples, of course, from astronomy, since that's what I know best, and two projects that I just happened to mention were LIGO and the gravitational waves, since Kip and Barry got their prizes from working on that at Caltech, and then the Event Horizon Telescope. And I didn't know that both Kip and Katie Bauman, who is on the Event Horizon Telescope project, is a new faculty member, assistant faculty at Caltech, were in the audience, and they both sent nice messages saying that they were so happy that they got mentioned in that context. At NSF, we call this working together across interdisciplinary boundaries Convergence, and it's really changed the way that we work and that we're funding now. Multi-messenger astronomy is a great example of this concept in action. Answers to big challenges can be addressed by widening our circle of friends and getting a lot more people at the table working together. I mentioned the example of numerical relativists on the LIGO team. So, you know, who knew? And as I said, came along just in time. NSF is also uniquely positioned to put this into action by building bridges across academia, government entities, industries, and other sectors. As astronomy and astrophysics build bigger and more sensitive telescopes, we'll need better and more efficient ways to manage them and process the data they produce. As seen by your presence tonight, Vera's legacy continues to be an inspiration to us all. She broke down many barriers. She was very frank. She was very direct. She was very targeted. Another thing that I talked about in my speech to the students was about the importance of focus. Vera was very focused. She would say, if there isn't a path, make one. I'm excited to see what the future of multi-messenger astronomy reveals about our universe. We're building on the foundation that Vera laid throughout her career, and I'm proud to be a part of that effort in my own way, from my own swim lane. I'm proud of how significant Vera's influence has been on our community and our discipline. And I very much hope that the answer to the riddle of dark matter will be solved before I take leave of the planet. So get going, everybody. Thank you. Sure, of course.
We want to solve before you leave the NSF.
So, are there any questions? Oh,
Michael.
Okay.
Michael.
France, do you care to comment? Do you care to comment on any of NSF's big projects? Under your tenure, you've had some great successes with the big facilities. Do you care to comment on any future big facilities that you see on the horizon? I mean, I know you talked about the LSST. Anything you see beyond that you think will transform astrophysics?
Well, DKIST, the Daniel K. Inouye Solar Telescope, is finished. They're in commissioning. It's on Haleakala on Maui. And so we should be seeing something spectacular from that pretty soon on the sun, which of course leads us to every other star. So yeah, I think that that's very important. And I think Texas, of course, we have a new investment in supercomputers. We have a number of them around the country, but I think the Frontiera supercomputer is going to allow, we saw excellent talks about simulations and all, and I want to learn more about where are the gaps. It's all about, so I think a lot of discoveries will come from there. I think one of the things that I learned from our analysis that led to the big ideas. First of all, why did we do them? We did them because Congress was not being very kind to us. We had, they were picking on individual grants and saying, why are you doing this? And this should be in waste books and all that kind of thing. Well, I'm very proud to say that this past year, but I will knock on wood, we had nothing in anybody's waste book. So we decided that we were tired of playing defense. Defense is a good position to play, and you got to play it well. We have a great public affairs unit, which every time they'd attack us, we'd put out, and it's all online, and I'd visit the congressman who put us in the waste book and say why this was not a waste and what its science drivers are and what its potential science is going to be, and then explain some things that when they were discovered, we had no idea where they would lead, but the results that they led to and so on. But we thought we needed a more offensive strategy, and so that was a strategy that led us to closing gaps in our funding, like the mid-scale research, like our includes gap, which is very much like Vera. It's about broadening participation of women and underrepresented minorities in science. Didn't talk about that, but that's understood in this audience. And about doing some big research ideas. So I think in the area of quantum information science, that's going to come along, and you know well from Chicago and the Chicago Exchange, they call it, that maybe David Oshalom there tells me maybe 5 years to get to a really practical quantum computer that can rival current classical computers, and then you've got a long ways to go after that. So there's a lot there. Of course, artificial intelligence, that's can yield all sorts of surprises, and we're heavily invested in that. And I would also cite the Arctic as a very, very important idea for investment because change is happening so fast there, and change to the inhabitants, change to the land, change to the entire planet because of feedback cycles and all. So there's the beauty of what we do as scientists and engineers is that we never know where the next discovery is going to come from. And we
Anything with
just have to do
silvered
it all.
glass?
Any what?
Anything with silvered glass?
Oh, so like, of course, yes, all right, okay, yes, like the giant segmented telescopes. Is this what you're you hadn't thought of that, Michael? Okay, so let me, that gives me the opportunity to give everybody a message here. So the Astronomy Decadal Survey has kicked off, right? And because I was at Caltech, I took the opportunity of having some private time with one of its leaders, Fiona. And it's just so important, I said to her, that you all think big. And in fact, my whole time, I also gave the Neugebauer lecture when I was there, and because Gary was a mentor of mine, I adored him, and they had this lectureship and it was called Thinking Big, and because that's what he did, and that's what all of you do. In your decadal survey, you have to not constrain yourself by historical limits of funding or what you think the funding limits are going to be. You should come out with the biggest, boldest, best ideas, because that's what sells. When we go to the Hill, or you go to the Hill, and you try to convince somebody to invest in something, it's the content that they get that seizes them, that they get. It's the imagination that you spark that really gets them excited. So I urge you that are contributing to the Decadal Astronomy Survey to think very, very big. And as far as the giant segmented telescopes go, we are, as you know, we're funding cost studies, and we're working very hard with the groups to define what are the next steps and so forth. But whether they make it or not is going to depend on how the whole community feels that they compare with every other really innovative project. They have to, they have to put out what's first, in big, and what's first in medium size, what's first in small. So I'm really looking forward to the results of that survey. That'll tell us the story, I think. Yeah.
Thank you for your leadership. As a young woman in astrophysics, it's really amazing to look at the head of the NSF and to see a brilliant woman. So I'm thankful for you. What are some of your guiding philosophies or principles as a leader throughout your career?
Oh gosh, I'm back to my last lecture at Princeton. Just to keep listening. I think the more you listen, lots of stuff just goes right over my head all the time. But the more I hear it, and the more I hear it from different people in different ways, all of a sudden, a spark just goes off, and I got it. I know what to do now. And so once you just have a lot of input, then all of a sudden your pathway just becomes a lot clearer. You can see what you really need to do. And I mentioned our example on the sexual harassment business. It was, after I read all these articles that were not so pleasant about people having real problems out there, and we had a giant group, all the assistant directors, all the heads of offices and everything, all sitting around the table. So, well, what can we do about this? And this is for universities to do. And then somebody in the group that is not a scientist but is a policy person and deals a lot with contracts and grants says, I know what we can do. And then it just sort of fell out from there. So I think whatever world you're working in, science or policy, leadership, administration, there are important things that you can do to move the ball forward. But you have to get a lot of input first from all kinds of people, your peer group, but students. When I talked with the students, the last message I gave them was that the biggest thing that I've learned from being a university president twice and department head and that sort of thing is that the young people, the students, emerging faculty, and so on, they just have a sense of the future. They have a better sense, I think, than anybody else, and I listen most carefully to them and where they think the future is taking us, and then I just try to follow suit, and that was certainly true at the university.
Any further questions? Okay, I think
Thank you.
we should thank our speaker.
Thank you. Thank you.